Okay, so we are required to determine the moment of the 650-pound force about point O and about point B. So the x component of the 650 is 650 cosine of 20 degrees. So we have 573.916. And the y component is 650 sine of 20 degrees. So we have 305.157 pounds. Now again, assuming counterclockwise moment as positive and applying your Varignon theorem. So let us try to resolve the force at this point. So we have your Fx and that is now your Fy. Now, let us try to get moment of the force F about point O. So again, the moment of the force F about point O, so your Fx is going counterclockwise about point O. So we have positive. Multiply this one by the moment arm. So this is the line of action of Fx, and the perpendicular distance from the moment center to the line of action is 4 inches. Fy is still going counterclockwise about point O. So it is positive. And the moment arm about point O, this is the line of action of Fy about point O, and the perpendicular distance from point O to the line of action of Fy is 10 inches. So we have 10 inches. Now, 573.916 by 4 plus 305.157 by 10, that is 5347.234 pounds. Now, the moment of the force F about point B. So your Fx is still going counterclockwise about point B. So we have positive Fx. And the moment arm of Fx about point B, so we have the line of action, so the perpendicular distance of the line of action to the moment center is 4 plus 10. So we have 14 plus Fy, because this is still going counterclockwise about point B. So the moment arm of Fy about point B, so this is now the line of action of Fy, and that one is equal to 6 inches. So we have 573.916 by 4 plus 305.157 by 10. So we have 9865.766 pounds. So again, this is a positive value, hence this is a counterclockwise moment, since we assume counterclockwise moment as positive. Okay. In 90, Newton force is applied to the control rod AB. So we have the control rod AB. Knowing that the length of the rod is 225 millimeter. So this length in here is 225 millimeter. Determine the moment of the force about point B. So we're going to determine now the moment of the force about point B. Okay, so this is equal to 25 degrees. Again, let us try to apply your Varignon's theorem. So let us try to resolve the components of this force 90 newtons in the horizontal and in the vertical axis. So I'm just going to consider now that this is the horizontal axis or your x-axis. So I'm going to consider that this is now the x-axis. And I'm going to consider that this one in here is now the y-axis. So that is the y-axis. So let's try to determine now the component of this force along the x-axis and along the y-axis. So your fx in here is equal to, so that is 90. Okay, so that is included. So we have cosine of 25 degrees. And this one is equal to 81.568 newtons. Hence, your Fy is equal to 90. So we have sine. That is not included in the y-axis. So we have sine. And this is equal to 38.036 newtons. Now, knowing now your x and y axis. So let us try to apply your Varignon theorem. So let us try to resolve the force at point A. So if you try to resolve the force at point A, so we have the rod in here. So this is now your rod. This is now your point A, and this is your point B. So I'm now going to resolve at point A. So your fx, so this is down to the right, so fx is going to the right, and fy is going downward. So this is now your f of x. And your f of x is now equal to 81.568 newtons. And we now have your f of y. So this is now your f sub y. And your f of y is equal to 38.036 newtons. Now, the rod is making an angle of 65 degrees with the horizontal. So this is therefore your rod, which is 65 degrees with the horizontal. So that is 65 degrees. And the length of rod AB is equal to 225 millimeter, or that is 0.225 meters, or that is equal to 0.225 meters. Now, so let us determine now this distance and that distance, so that we will know the moment arm of fx and fy. So this is your rod AB. So that is A, and this is now your B. So it makes, so this is 65 degrees with the horizontal. So this is now 65 degrees with the horizontal. So I'm going to consider this distance in here to be x distance, and I'm going to consider that that one is equal to y, that is 225 mm. Now, so that if you will going to get cosine of 65 degrees, this is equal to x all over 225 mm. So the value of x in here is now equal to 95.089. That is 95.089 millimeter. Next, Let's try to determine now y. So if you're going to get sine of 65 degrees, so this is equal to y all over 225 mm. So the value of y is equal to 203.919 millimeter. Therefore, this distance now is now your y. So this is now your y. And your y is now equal to 203. So this is now equal to, that is 203.919 mm. And this is the distance x. So we now have your x. And your x in here is now equal to, this is equal to 95.089 mm. It's 95.089 mm. Now, again, let us try to get moment about point B. So the moment of the first F about point B, assuming counterclockwise moment as positive. So let's try to assume, assuming again counterclockwise moment as positive. Now, the moment of the first F, therefore, about point B is now equal to the moment sum of its components about point B. So this is the moment center. So Fx is going clockwise about point B. So it is negative since we assume counterclockwise as positive, minus Fx and the moment arm. So this is now the our moment center is at point B, and that is therefore the moment R. So that is perpendicular to Fx, which is equal to 2. Okay, so in meters, this is equal to 0.203919. So that is in meter. Now, the moment of Fy about point B is now going counterclockwise about point B. So plus Fy. And this is 95.089 mm, or that is equal to 0.095,089 meters. Okay, 0.89 meters. So we now have the moment of the first F about point B is equal to 81 minus 81. This is minus 81.568 by 0.203919 meters. Okay, plus Fy. So this is 38.036 newtons by 0.095,089 meters. Hence, the moment of the first F about point D is negative 13.016 Newton meter. That is in Newton, this is in meter, so we have Newton meter. What does the negative sign indicates? So, the negative sign, therefore, indicates that the moment of the force about point B is 13.016 Newton meter. That is now a clockwise moment. Now, so this is your rod AB. So we have the rod AB. So this is your point B. It makes an angle of 65. It makes an angle of 65 degrees with the horizontal. So this is now your 65 degrees. So we now have your point A. So at this time, I will now going to use AB as an axis. I'm going to rotate. So if I will going to consider that this is now the x-axis. So ito yung x prime natin. So I'm just going to get x prime axis. So that is your y prime. And then perpendicular to y prime is x prime. So this is now your x prime. Now, so I'm going to use x prime and y prime axis. So we have the x prime axis and we have the y prime axis. So this is now the y prime axis. So I'm going to consider this is now your y prime. And this is therefore your perpendicular is now the x prime axis. This is now your x prime axis. Now, so in this case, let us try, I will going to consider that this one in here is an angle theta. I'm just going to consider that this angle in here is an angle theta. So I'm going to consider that one is an angle theta. So what is therefore your angle theta? Okay, up to that point is an angle theta. So your theta in here is equal to, so you try to take note that your theta is now equal to 65 degrees. You try to take note, ito yung x natin. That is your x. So this is an angle theta, and this one is equal to 65 degrees, which is now your angle theta. And the first F in here is now at this point in here. So I'm going to write the first F. So ito ngayon ang first F natin. So this is your first F. So this is now your first F, which is equal to 90 degrees. And it makes an angle of 25 degrees with the horizontal. 25 degrees with the horizontal. So if I will now going to consider that this angle in here, so this angle is now equal to beta. So your beta is now equal to 65 degrees minus 25 degrees. And that one is equal to 40 degrees. Now, I will going to redraw this axis in here. So, we have the rod AB. So, again, this is your rod AB. So, this is now your A. This is your point B. And this is now your point A. At that point is now your point A. Now, so we have now we now have the axis. So this is one is parallel along the rod AB, and that is now again your y prime axis. And perpendicular to the y prime axis is now your x prime axis. That is your x prime axis. Now, so that the first F, so the first F is now making an angle beta with the y prime, and that is equal to 40 degrees. So this is now your F. So this is your F, which is equal to 96 newtons. So this is now making an angle of 40 degrees with AB. So that's 40 degrees with AB. I'm sorry, this is 90 newtons. 40 degrees with AB, which is now your beta. So let us try to determine now the component of this force in the x prime and in the y prime axis, so that your F x prime is now equal to 90. That is now sine of 40 degrees. We use sine again because this 40 is included in the y prime axis. And this one is equal to 57. So we have 57.851 newtons. 57.851 newtons. And then next is now your Fy prime. And your Fy prime is equal to F 90 cosine of 40 degrees. 90 cosine of 40 degrees is now equal to 68.944 newtons. So that is 68.944 newtons. So, applying now your Varignon's theorem. Let's try to apply your Varignon's theorem. Again, this is now your rod AB. So this is now the rod AB. So we have, this is your point B. And then we now have your point A. So your y prime is this one. So we now have again the y prime. This is your y prime. Perpendicular to the y prime is now your x prime. Okay, so that is now your x prime. So I'm going to extend this y prime in here. Okay, so that is your y prime. Okay, so again, this one in here is 90 degrees. So we get already the components of the force in the x prime and in the y prime axis. So this is your x prime. So this is now your Fx prime. Okay, so that is down to the right. So this is going to the right. So that is now your Fx prime. And then we now have your Fy prime. So this is now your Fy prime. We now have Fy prime. Now the length of the rod. So the length of the rod AB is your length AB is equal to 225. So that is equal to 225 millimeter. So still assuming counterclockwise moment is positive, then the moment of the force F equal to 90 about point B is now equal to the moment sum of its component. So your Fx is going clockwise. So we have minus Fx prime. Multiply this one by the moment arm. So that is the perpendicular distance from the moment center to the line of action of the force Fx prime. So that is 90 degrees, it is perpendicular, hence this one in here is 225 millimeter, or that is equal to 0.225 meters. Now, your Fy prime, you try to take note again that Fy passes through your moment center. Hence, it has no moment arm. The moment arm in there is equal to 0. Therefore, Fy prime has no moment about point B. Again, you take note, always take note that if a force passes through the moment center, then its moment is equal to 0. So this moment ng MB is minus, and your Fx prime is 851 newtons. Multiply this by 0.225 meters. And this is therefore equal to negative 13.016 Newton meter. Again, what does the negative sign in here indicates? So it indicates, what does the negative sign in here indicate? So it indicates that the moment of the force F about point B is a clockwise moment. Since we assume counterclockwise moment as positive. Okay, next. A force P acts in the XY plane. The moment of the force P about points O, A, and B are 80 Newton meter, negative 200 Newton meter, and 0 respectively. Determine the value of P. So let's try to determine now the value of P. So let us try to have, or at this point, I will going to assume, okay? Again, assuming counterclockwise moment as positive, then the moment of the force P about point O is equal to 80 Newton meter. That is 80 Newton meter. So we have counter. And then the moment of the force P about point B, about point A, the moment of the force P about point A is equal to negative 200 Newton meter. So this is clockwise. And the moment of the force P about point B is equal to 0. Now, you try to take note that, or since the moment of the force P about point B is equal to 0. Hence, the force P passes through point B. Okay, so hence, the force P passes through point B. So, we now have the force P. So, it passes through point B because the moment is equal to 0. So, we now have the line. So, this is the line of action of the force P. Now, if I will going to resolve the component of the force P at point B. So, I'm going to resolve the component. So, this is the component of the force P in the x-axis. So, I'm going to consider that one as Px. And this one in here is now the component of the force P, the component of the force P. Okay, I'm just going in the y-axis. So, the component of the force P in the y-axis. I'm just going to consider this is now against point B. Px, okay, I'm going to assume that Px is going to the left. So, that is now your Px. Now, let us try to get now the moment of the force P about point O. So, the moment of the force P about point O is now equal to applying your Varignon theorem. About point is now equal to the moment sum of its component. Hence, your Px passes through your moment center. Hence, the moment of Px about point O is equal to 0. And we now have your Py is counterclockwise. So, this is counterclockwise about point O. So, we have positive Py. That is positive Py. Multiply this one by the moment arm or the lever arm. And the moment arm is now the distance from the moment center to the line of action of the force. So, that is the perpendicular distance. And 400 mm is equal to 0.4 meters. Now, the moment of the force P about point O is counterclockwise, so that is 80 Newton meter. And that one is equal to Py multiply this by 0.4. Hence, your Py in here is now equal to 80 all over 0.4. And that one is now equal to 200 newtons. So, we get a positive value. Therefore, the assumed direction of Py is correct, and that is going upward. Next condition is that the moment of the force P about point A, moment of the force P about A, and that one is now equal to, so that is equal to, so about point A, Px is going clockwise about point A. So, we now have Px and minus Px, and the moment arm is 500 mm, or that is 0.5 meters. So, that one, 0.5 meters. So that is going clockwise. Okay, so we now have plus. We have plus py, so that is going counterclockwise. Plus py, multiply this one by the moment arm with about point A, and that one is equal to 0.4 meters. So that is equal to 0.4 meters. So this is equal to negative 200. So that is equal to minus 0.5 minus 0.5, multiply this one by px. So we have minus 0.5, multiply this one by px, plus py. So plus, so your py in here is, no, okay, so we get, so your py is equal to 200 multiply this one by 0.4 meters. So it's 200 multiply this one by 0.4 meters. So we have minus 200 minus, transpose this, so that is 200 by 0.4 is now equal to 0.5 px. So it's equal to 0.5 px. So this is equal to minus, okay, so we have minus 280 is minus 0.5 px. So minus 280 is equal to negative 0.5 px. Hence, your px is now equal to minus 280 all over minus 0.5, or that is equal to 560. So it's equal to 560 newtons. Since we get a positive value, therefore, the assumed direction of px is correct, and your px is now going to the right. Now, let us try to determine now the value of P. So the value P, or the magnitude of P, is now equal to the square root of px squared, 560 squared, plus py squared, 200 squared. And that is equal to, so the value P is 594. So we have 594.643 newtons. Okay, 594.643 newtons. So let us try to determine now the angle it makes with the x-axis. So I'm just going to consider. Now, so your force P therefore in here, since this is upward and this is now going to the left, hence this is now the force P. That is your force P. So let us try to determine now the angle it makes with the horizontal. And this is now an angle theta. So your theta, so we have again tangent of theta is equal to py all over px. So we now have your theta is now equal to the arc tangent of py over px, and that is equal to the arctangent of py. So that is 200 all over 560. So your theta in here is now equal to 19.65 degrees. So 19.65 degrees. Okay, now at this time, let us try to assume clockwise moment as positive. So this one, clockwise moment as positive. So let's try to assume clockwise moment as positive. So again, let us try to resolve the component of this force in the x-axis and along the y-axis. The moment of the force P about point O is 80 newtons. So at this point, let us try to consider clockwise moment as positive. And the moment of the force P about point A is negative 200. So this is counterclockwise moment. Again, the moment of the force P about point B is equal to 0. So again, the force P passes through point B. And let us try to resolve again the components of this force at point B. So we now have moment of the force P about point O is equal to, so we're getting moment. So again, Px has no moment. So that is now Px that is 0 because it passes through point O. Since we assume clockwise moment to be positive and Py is going counterclockwise, hence that is negative, Py multiply this one by the moment arm, which is 400 millimeter, or that is 0.4 meters. Now, the moment of the force P about point O is 80 Newton. So that is 80 Newton, so it's counter, so that is negative. So that is 80 Newton meter. And this is equal to minus Py multiply this by 0.4. So your Py is equal to negative 200 newtons. Hence, Py is equal to 200 newtons. So we assume this to be going upward. Therefore, that is going downward. So that is negative 200 newtons. Now, the moment of the force P about point A is now equal to, assuming clockwise moment as positive, Px is going clockwise. That is positive Px. Multiply this one by 500 mm or 0.5 meters. And then Py is going counterclockwise. So that is minus Py multiply this one by 0.4 meters. Hence, the moment of the force P about point A is 200 Newton meter. So your 200 Newton meter, since we assume clockwise, so ang 200 Newton meter natin dito will now become negative 200. And that is equal to 0.5 Px minus 0.4, and your Py is negative 200. You try to take note that we will be using negative 200 because we did not change the direction, although we know it is going downward. So, negative 200 Newton. So, we now have minus 200. That is minus and minus is plus, so minus 0.4 by 200 is equal to 0.5 px. So we now have negative 280 is now equal to 0.5 px. Hence, your px in here is equal to negative 560. So that is negative 560 newtons. Hence, px in here is equal to 560 newtons. Okay, we assume this to be going to the left, and therefore, that will go to the right. So, if we assume clockwise moment to be positive, your P is going down to the right. However, the magnitude of P is still equal to the square root of Px, 560 square, plus 200 square, or that one is still equal to 594.643 newtons. Okay, and the angle it makes with the horizontal. So, this is now your, okay, this is your O, and this one is now your Y, and that is now your X. So let us consider this is now your point B. So that is your point B. So the first, when we assume clockwise moment as positive, then this is down to the right. So this is therefore down to the right. And this is therefore the first P. So that the angle it makes with the horizontal theta, your theta is still equal to the arctangent of Py all over Px. And this is equal to the arctangent of Py, which is 200 all over 560. That is equal to 19.65 degrees. So 19.65 degrees. So you try. Okay, so this is therefore the angle that your P makes with the x-axis. Okay, you try to take note that when we did assume that the moment of the when we did assume counterclockwise moment as positive, your P is up to the right, and it makes an angle. Your P is up to the right. And if we try to consider, or we did assume clockwise moment as positive, your P is up to the left, your P is down to the right. Now, you try to take note that the magnitude of P is still the same. Next, determine the direction theta of the 40-pound force F, so that force F produces the maximum moment about point A. Compute the maximum moment. Again, let us try to apply again your Varignon theorem. So if I will now going to consider that this is the y-axis. So this one in here is now the y-axis, and this one in here is the x-axis. Let us try to determine the component of the force F along the y-axis and the component of the force F along the x-axis. Now, your Fx is equal to, so that is going to the right, so we have 40 cosine of theta. And your Fy is equal to 40 sine of theta. So that is the component of the force F. Now, the moment of the force F about point A is maximum. So how are we going to determine angle theta and the maximum moment of the 40-pound force? Okay, so again, let us try to apply your Varignon's theorem. So this is again. Okay, so again, this is your, so we have the wall in here. Okay, so this is now your point A. So this is 8 feet, and this one is 2 feet. So the x component, this is down to the right. So we have Fx is going to the right. This is your Fx. So Fx. So we have down to the right. So Fy is going downward. So we now have your Fy. The moment of the force F about point A. So moment of the force F about point A is now equal to the moment sum of its components. So we have, at this point, I will now going to assume. So I'm going to assume. So let us try to assume clockwise moment as positive. Assuming clockwise moment as positive. So therefore, the moment of the force F about point A is now equal to, so this is, Fx is going clockwise about point A. So we have positive Fx, now the moment arm. So this is the line of action of Fx. So that is perpendicular from the moment center A, which is equal to 2 feet. Fy is going clockwise about point A, so that is still positive. Fy multiply this one by 8 feet. So the moment of the force F about point A is now equal to Fx. That is 40 cosine theta, multiply this by 2, plus 40 sine of theta, multiply this one by 8. Or this is equal to 80 cosine of theta plus 40 by 8 is 320 plus 320 sine of theta. So 320 sine of theta. So let us try to determine the direction angle, which is equal to theta. Okay, so again, for maximum moment, we have to set the first derivative of the moment of the force F about point A with respect to theta equal to 0. So you have to set the first derivative of the moment of F about point A with respect to theta equal to 0. So your derivative of the moment of the force F about point A with respect to theta is equal to 0. 1 is equal to 0. And this is therefore equal to, so we have the moment of the force F about point A, 80 cosine of theta. So that is 80, the derivative of cosine theta is negative sine of theta, plus 320. The derivative of sine of theta is equal to cosine of theta. Cosine of theta. So that is equal to 0. So we now have 80, transpose this to the other side of the equation, 80 sine of theta is now equal to 320 cosine of theta. So it's 320 cosine of theta. So we now have your sine of theta over cosine of theta is equal to 320 all over 80. So sine theta over cosine of theta is now equal to tangent of theta. And that is equal to 320 all over 80. So that your theta is now equal to the arctangent of 320 all over 80. Hence, the value of theta is 75.96 degrees. Now, I will consider this one to be equation 1. So from equation 1, the maximum moment of the force F about point A is now equal to 80 cosine of 75.96 degrees plus 320 sine of 75.96 degrees. So the maximum moment of the force F about point A is equal to 329.848. So the unit of the force is pound and the unit of the distance is in feet. So that is pound, foot, or foot pounds. That is the maximum moment of the force F about point A. Okay, next. Determine the total moment of all the forces about point A. So this is your point A. So this is your, let's consider 180 Newton here as F1, 180 Newton in here as F2, your 160 Newton as F3, and your 150 Newtons as F sub 4. So again, let us try to determine the X and Y components of F3 and F4. Your F1 has no Y component because it is horizontal. And your F2 has no Y component because that is horizontal. So that is when the axis, when the horizontal, the axis is vertical and horizontal axis. So I'm just going to consider that this is now the y-axis and this one in here is the x-axis. So we now have the x-axis. So the component of F1 in the y-axis is 0 because it is along or parallel to the x-axis. And the component of F2 in the x-axis is also equal to 0 because this is parallel to the y-axis. So only F3 and F4. So we now have your F3x is now equal to 160 sine of 30 degrees. 160 sine of 30 degrees. And this is equal to 80 newtons. Your F3y is equal to 160 cosine of 30 degrees. So we have 138.564 newtons. F4x is equal to 150. So the slope of F4 is 3 vertical to 4 horizontal. So the hypotenuse of the slope triangle is equal to 5. So that's 150. Multiply this one by 4 all over 5. And this is equal to 120 newtons. And your F4y is equal to 150. We have 3, so we have vertical over the hypotenuse of the slope triangle. And this is equal to 90 newtons. Let us now apply again your Varignon's theorem. So applying again your Varignon's theorem, so we now have this is. Okay, so we have okay, let's try to draw the figure. Newtons. So we have that is F2. This is your F1. And that is equal to 180 newtons. So we have this is your point A. So we have 250 mm. And this one is 250 mm. This is 250 mm. and this one is 350 mm. So there's your point in here. So I'm just going to use red. So we have your fx. Okay, so this is now your fx. f3x. So we have your f3x. That is down to the left. This is your f3y. f3y. So let's try to have now your f4. So we have f4y is now your f4y. So again, it's still down to the right, and we now have your f4x. This is your f4x. Okay, so we have now the distances, 300 mm from this point, 300 mm. So this one is 200 mm. So all in all, that is 500, that is 250, and therefore, this one in here is 250. Now, this one in here is 200 mm. That is 200 mm. So I have 250 plus 350 is 600. Hence, this distance in here is, okay, so that distance, I'm going to place F3y in here, is F3y. So this distance in here is now equal to 400 mm. Equal to 400 mm. So applying now the your Varignon theorem. So the moment of all the forces about point A, F1, F2, F3, and F4 is equal to the moment sum of each components of all the forces about point A. Now, so at this point, assuming clockwise moment as positive. So assuming clockwise moment as positive, then we have, let's start with F1. So F1 is going counterclockwise. So it is negative F1. Multiply this one by 250 mm, or that is 0.25 meters. Now, F2 is going clockwise about point A. So we have positive 100 F2. Multiply this one by 0.25 meters. Okay, F3x is going clockwise about point A, so it is positive F3x. And the moment arm is 400, or that is 0.4 meters. Your F3y is also going clockwise about point A. So it is positive F3y. And the moment arm is 500 mm, or that is 0.5 meters. F4x is going clockwise about point A. So that is again positive F4x. The moment arm is 600 mm, or that is 0.6 meter. And your Fy is also going clockwise about point A. That is positive F4y. Multiply this one by 300 mm, or that is 0.3 meters. So this is now the moment of all the forces about point A. So that is the moment of all the forces about point A. So let's try to substitute values now. So the moment of all the forces about point A is F1. So we have 180 by 0.25 plus F2 is 180 by 0.25. F3x is 80. So plus 80, multiply this by 0.4. Plus F3y is 138.564, multiply this one by 0.5. Now plus F4x is 120. Multiply this by 0.6 plus F4y, which is 90, multiply this one by 0.3. So the moment of all the forces about point A is equal to, so this one is now equal to 200.282. So that is 200.282. So the unit of the force is Newton and the distance is in meter. So that is Newton meter. Since we assume clockwise moment as positive, hence the net moment of all the forces in this system about point A is clockwise moment.